Hey there, chemists. Welcome to another exciting lesson in chemistry. Today we're going to be continuing our discussion about equilibrium, but we're going to spend some time over the next couple of days focusing on what happens when we take a system that's in equilibrium and we mess around with that system. And so let's go ahead and take a look at a quick demonstration. So what we see here in this video is that we actually already have a solution that's at equilibrium, that pink solution. And to that solution, we're adding hydrochloric acid. Let's go ahead and take a look at what happens. So note that as we added the hydrochloric acid, it caused our solution to turn blue. Let's go ahead and add water and observe what happens. Okay, addition of water causes our solution to turn pink. Addition of HCl causes it to turn blue, and so on and so forth. So let's go ahead and take some time and go ahead and jot these down in our notes. Okay, so record observations from our video. So what did we see here? We saw that we had a pink solution in equilibrium. Okay, and with the addition of HCl, it turned blue. And with the addition of water, it turns back to pink. And so what we're going to look at today is how did that addition of those different substances, the hydrochloric acid and the water, how did that change our system, and why does it cause it to shift to blue and pink? What's causing that color change? So just as a quick refresher, how do we define equilibrium? What does it mean for a system to be in equilibrium? It means that two opposing processes, okay, occur simultaneously, okay, at the same rate. So again, we've focused heavily on this equilibrium, the equilibrium between the synthesis of N2 and H2 to produce NH3, which is in equilibrium with the decomposition process of NH3 forming N2 and H2, or nitrogen and hydrogen gas. Okay, so we have these two processes, synthesis, decomposition, they occur at the same rate, and they're happening at the same time. Now that we have this idea of equilibrium, I want us to kind of think of our bodies as a state of equilibrium, okay? And this is something you should be kind of familiar with from your living environment or biology class, this idea of homeostasis, okay? Now, suppose that you were asked to run a half marathon, okay? And if you aren't familiar with what that is, that's 13.1 miles of running in one stretch, okay? In fact, I ran one in Arizona and it was so hot. It was just insane. I can't do that ever again. But let's say we were running this half marathon. How does your body respond to this stress, this idea of running for 13.1 miles? One big thing that's going to happen is that your body is going to sweat. What is the purpose of your body sweating as you are running? Well, the idea is that your body sweats in order to cool itself down. Your body's overheating and it's trying to avoid that overheating by sweating, which cools your body down, right? Which absorbs some of that heat energy. So your body is going to sweat, and this is to maintain or reestablish, I just spelled this wrong, reestablish, okay, homeostasis. Okay, this idea of this bodily equilibrium. So our body is in equilibrium. We run 13.1 miles. We stress our body out by doing that. And what our body does is it counteracts that stress by sweating and reestablishes this equilibrium in our body. And the same thing is going to be true for chemical equilibrium. If our system is at equilibrium, then if we stress our system is going to try to counteract that stress and maintain equilibrium or reestablish an equilibrium. So how were we stressing our solutions in the video? Well, in the video, what we were doing was adding additional substance or additional reactants or products, okay, into our already established equilibrium. So we were adding more reactants or products into our equilibrium, okay? So let's go ahead and jot that down. So we added or changed the concentration of our reactants or products. Okay, so let's think about this chemical equilibrium that I've provided for you on this sheet. We have the reaction between A and B, and when A and B collide, they create C and D. Now, C and D also, right, it's in equilibrium, so C and D are also colliding to form A and B. So what's going to happen if we add additional A, okay? And a lot of today's lesson is going to have to really be putting on our conceptual thinking cap. We have to sit here and envision what would happen in terms of collisions if we're adding additional A. So if I add solute A or substance A into my reaction chamber, what's going to happen to the number of collisions between A and B? Okay, if there's more A present, then A and B are going to collide more frequently. So as we increase the concentration of A, there is an increase in the number of collisions between A and B, causing an increase in the forward reaction. Okay, so basically we have A and B colliding more frequently. It causes this momentary increase of that forward reaction rate. Now, think to yourself, eventually, if I'm producing more C and D because I have an increase in the rate of my forward reaction, what's going to happen to the rate of my reverse reaction? Well, eventually, it's going to equalize out again, right? Eventually, C and D will collide more frequently, producing more A and B, and eventually they'll reach a point where they reestablish equilibrium. But in that momentary addition of A, we create a push of the forward reaction, okay? So understanding that, let's go back and look at what we saw from the video, okay? So we have here a fairly complex equilibrium system, or like a very kind of scary equilibrium, but it's not that bad. We just have two complex cobalt ions, okay? Cobalt is CO, so those two scary looking ions, the COH2O6 2 plus and the COCl4 2 minus, those are your complex cobalt ions, and we have chloride and water. Okay, now thinking back to what we had seen, we saw that addition of HCl turns it blue, addition of H2O turns it pink. So interestingly, these two cobalt ions, transition metals, and remember transition metals are special because they can create colored solutions. Each of these cobalt ions is a different color. So we have the cobalt chloride with the 4 minus 2. This is a blue ion. Okay, this is a blue ion. Okay, our cobalt 6H2O, this is a pink ion. Okay, this is a pink ion. So what we saw, again, as a reminder, is we added hydrochloric acid, or HCl, and we saw our solution, turn from pink to blue. So why is that the case? First and foremost, let's just start with what does the addition of HCl really mean? Looking at our equation, we don't see HCl anywhere in that equation, so I can't even use this thought process of A plus B becoming C plus D, this idea of adding more A. Okay, we need to talk about HCl. HCl is an acid, and we'll talk a little bit more about this in our next unit, but this acid actually dissociates or breaks apart in solution into H plus aqueous and Cl minus aqueous ions. So from your reaction that's provided here, when I'm adding HCl, what I'm really adding is additional chloride ions, right? So our ions in our equation, we've removed the H plus ions because they don't impact our chemical reaction in any way. But when I am adding this HCl, what I'm really adding is this Cl minus ion. Okay, so as I add HCl, I am increasing the amount of this chloride ion. Okay, and what's happening then? Okay, why would it turn blue? Well, by adding chloride, I'm creating an increase in the number of collisions between chloride and COH2O6 2+, and when those two collide more, the rate of our forward reaction increases, okay? And as a result of that forward reaction increase, we produce more of our COCl4, okay? So as we add HCl, which is again the same thing as adding Cl minus, we increase the number of collisions between COH2O6 2+ and Cl minus, okay, which increases the rate of the forward reaction, producing more COCl4 2-, which is again blue in color. Okay, so you have to think each time we talk about addition of one of our substances, how is that impacting number of collisions? Is it causing an increase in the forward reaction or an increase in the reverse reaction? And is it producing more or less of each of these ions? This idea is called Le Chatelier's principle, okay? If a system in equilibrium is subjected to a stress or some form of disturbance that upsets the equilibrium, the system responds in a direction that counteracts the disturbance and restores the equilibrium, and that's called a shift. So in the example we just saw, we added to our reactant side, and it caused the forward reaction to increase in its rate. Okay, when we have an increase in the forward reaction, we call that a shift to the right. Okay, aka we are causing the rate of the forward to increase, so we're producing more of the substances to the right. If we were to do something in the opposite direction, right, what are we doing? We're increasing the rate of the reverse, and therefore that would be considered a shift to the left. It would cause the reverse reaction to increase, creating more of our reactants. So when we add water to the solution, which way does it cause a shift? Okay, when we add water to our system, I want to use a different color. Let's use this light purple. Okay, when I'm adding water, so I'm increasing the amount of water that I have, what happens? That causes an increased number of collisions between the water and our cobalt chloride 4,2 minus, COCl4, which causes the rate of our reverse reaction to increase, producing more of the chloride and more of the pink ion. Okay, hence why when we added water, it turns pink. So if water is added to the solution, in which way does it shift? Okay, if H2O is added, the reaction shifts. Okay, and again, we increase the rate of the reverse, so that's a shift left. Okay, there's an increase in the number of collisions of the products, increasing the rate of the reverse reaction, or a shift to the left, producing therefore more of our reactants. Okay, so to kind of summarize this up, what I'd like to do is I'd like to take some time to just look through a couple of examples and see how this impacts everything. This is going to be a slightly longer video. I do apologize, but the next 2 days videos should be short since we're going to be talking about Le Chatelier's principle for 2 more whole days. So again, I've given us our blank slate of equation here. We're going to talk about 3 different stresses to our system and how that's going to impact our reaction. So the first one that I want to do is I want to focus on our stress being an increase in the amount of the COCl4,2 minus. So my stress is increasing the amount of the COCl4,2 minus. Okay? If I increase the amount of that, which direction is that going to cause the reaction to shift towards? Is it going to shift to the left or will it shift to the right? Okay, it's going to shift to the left direction. Okay, now these symbols, this hard bracket right here, this represents concentration. And so what I'm asking here is, what is that shift's impact on the concentration of these 4 different substances? Meaning, when I have that shift, will it increase my concentration or decrease my concentration? And here's where you have to put that, that conceptual thinking cap on. So let's first start with COCl4. So we've increased the amount of COCl4. Okay, anytime we're talking about whatever our stressor is, I like to call that the plateau, and we'll talk a little bit more about why that is in a moment. But what we're going to do is we're going to increase our COCl4, and as a result, there's going to be an increase in the number of collisions between the COCl4, 2 minus, and H2O. So we're going to be making those 2 collide more often. So what do you think happens to the amount of water that we have then? If COCl4, 2 minus, and water are colliding more frequently, that means the amount of water that we have is going to decrease because it's being used up to create an increase in this rate of the reverse reaction. The reason we say it plateaus for COCl4 is because when you add it to solution, we're going to add it, but then it's going to get used up. So I like to say, for the purpose of making it easy, that it's kind of a plateau. We add it, it goes up, we use it up, it goes down, and so we kind of break even. Well, okay, let's talk about the concentration of both Cl4 or COH2O6 2 plus and Cl minus then. If we've increased the rate of our reverse reaction, that means that we should be producing more of each of these. So we have an increased concentration of this and an increased concentration of this. Okay. What happens then? Let's do a different one. What happens if I increase the amount of COH2O 6,2 plus? Okay. So now I've increased my concentration of my cobalt water 6,2 plus ion, which is going to create an increase in the number of collisions between Cl minus and CO H2O6 2 plus. Okay, and therefore the reaction is going to shift to produce more of these two products. So our reaction shift is to the right. We're talking about cobalt water 6 2 plus, so we're going to say that breaks even. What happens to the amount of the Cl minus? If I'm increasing the number of collisions between that cobalt ion and the chloride, we're going to decrease the amount of chloride because we're using it up with our extra cobalt that we've added. As a result, remember, we've shifted our reaction to the right, and because the reaction is shifted to the right, we are producing more of this and more of this. The last one that I want to go through quickly with you guys would be a different situation. So thus far, we've talked all about adding, when we add stresses or when we add more concentration to solution, what happens? But it is possible to remove substances from solution. So let's suppose that I remove chloride ions from solution, okay? So I remove something from solution, your system wants to make up for that, and your system wants that in your solution, okay? Or like hypothetically, if we're talking about, let's say you are really, really, really hungry, or you aren't able to eat, and your body, in order for your body to maintain homeostasis, you do need to eat, okay? So what does your body do? How does it counteract that stress of not eating? Well, there's a couple things, right? It'll start to eat away at your stored fats. That way it can make up for the loss of that food, right? Or the loss of you not having food. So if I remove these chloride ions, then my system wants to make up for that and produce more chloride ions. So how do I produce more chloride ions? Well, you can increase the rate of your reverse reaction, right? If I increase the rate of my reverse reaction, then I will produce not only more chloride ions, but more cobalt water 6,2 plus ions. So which direction then is that a shift in? That's a shift to the left, okay? As a result of that, I'm not only producing more chloride, but also more cobalt, okay? We were talking about chloride, so we're going to say that breaks even. And then for the other two, we're shifting away from that, which means that we are using the cobalt chloride 4,2 minus, and we are using water to make more of our chloride and cobalt water 6 plus. So those concentrations decrease. Once you've done a lot of these problems, they will start to become second nature to you. We're gonna practice obviously a bunch in class tomorrow, and we're gonna use these questions tomorrow at the beginning of our lesson to help us kind of solidify our understanding. And once we've got a good solid understanding, I can try to help teach you some shortcut ways to figure these things out. Thank you guys for paying attention. I do apologize for the length. Tomorrow will be shorter. Have a great rest of your day, and I will see you guys tomorrow.